Good morning, everyone. My name is Taimur Bakshi, and today I will be talking about our research work on anomalous host identification in high cardinality network streams using adaptive reverse sketching. To give you an overview of this research work, I will talk about anomalous host identification, including popular techniques and inherent limitations. The methodology followed in present work will detail adaptive reverse sketching, cardinality estimation for abnormal host identification, and machine learning based filtering to reduce the storage of traffic data. I will then discuss the testbed setup and the results from a quantitative as well as qualitative perspective. This will be followed by a summary and a conclusion. So let's start with anomalous host identification. Or security and network analysts rely on correlated network traffic and system telemetry data for threat and vulnerability identification. Accurate monitoring is essential to identify malicious host behavior in real-time incident management as well as threat mitigation. The cardinality factor of a network host is generally recognized as an account of host communications over a particular time bin, with the underlying relative changes in consecutive measurements illustrating minor or major cardinality variations. So, hosts depicting high cardinality changes are usually referred to as super or abnormal hosts, and they require timely identification to limit and curtail any malicious operation going on in the network. The existing approaches primarily rely on sampling and sketching techniques to identify anomalous hosts that exhibit significantly large changes in network traffic. Now, service providers and large data centers generate big volume network data, thereby constraining your memory resources and limiting identification accuracy. Similarly, certain types of attacks such as distributed denial of service and targeted APTs, advanced persistent threat campaigns, can lead to noticeably large cardinality variations across varying timelines. And this can lead to memory wastage and reduced overall normal and abnormal host discrimination accuracy. So, although existing schemes seek to identify and relate abnormal hosts primarily using flow sampling, host behavior, and cardinality changes, or a combination thereof, the inherent issues such as duplicate packet counting and impractical memory costs while monitoring a large number of connections over a much smaller time frame require a more updated and flexible approach. So, to overcome these difficulties in timely abnormal host identification, the present work proposes a novel approach to simultaneously measure cardinality changes between consecutive time bins using reverse sketching from a network wide monitor for sources and destinations. To maximize memory economy, a simple 2D bit array comprising a different number of rows and columns is employed to collect cardinality information pertaining to each network host. And then machine learning is used to compute time bins for analysis using lower values for low cardinality hosts and adaptively extending bins for high cardinality hosts according to real time traffic conditions. So, coming to the present methodology, device monitoring agents are used to extract information from packets and flows and then compress them into data structures represented by age and transmit them to analytic servers. To optimize memory usage in the present adaptive reverse sketching scheme, data structures are deleted from network switches after transmission, allowing the next packet or packet stream for examination and processing. And abnormal hosts are identified as malicious agents as well as victims by accounting for the cardinality changes exceeding a predefined threshold over consecutive time bins such as T1 to N. For each packet P traversing a network switch represented by I, the packet stream P of I is examined over T by recording tuples, two pieces of information, where eta denotes the flow label and sigma denotes the individual packet elements such as source, destination, addresses, ports, and protocols. To generate reversible sketching, the data structure H provided by the device I is considered as a two-dimensional bit array, H of I, Jk. And the cardinality estimation in adaptive reverse sketching, or ARS, seeks to improve the memory footprint by incorporating ML-based filtering to eliminate the storage of nodal information predicted to have low cardinality. So ML-based filtering is employed to reduce the storage of traffic information with a lower cardinality attribute by predicting the value of beta and the cardinality change delta gamma threshold alpha, which is predicted to classify the abnormal host. Afterwards, we use a C5 decision tree for training and classification of these thresholds. A smaller traffic sample W is taken from a network trace to compute H. And subsequently, we use offline analysis using automated DDoS, which is a malicious packet recognition tool, to label the respective H, normal or being malicious. And the label data is afterwards used to train C5 to predict alpha and beta to be used for subsequent traffic analysis. So to evaluate the performance of the ARS system, experiments were performed systematically on research test network traffic data and a Al-Qaeda DDoS attack 2007 set. And the results were compared with CSE, DCDS, and RVCDS methods. CSE detects port scans and DDoS using source and destination spreading estimates, whereas DCDS and RVCDS identify abnormal hosts by measuring the connection degree changes over a specific measurement period. All of these experiments were conducted using a Jupyter notebook on a PC with 64-bit Linux OS and a Core i7 CPU with 8 GB of RAM. Two traffic captures were collected between 22nd of January 23 and 24th of January 23 at our university campus during normal teaching hours. These sets were further analyzed to account for any static and dynamic IP addresses used, and malicious packets were identified using offline traffic identification. The relevant packets were subsequently labeled to specify the normal and attack traffic for C5 training. And the specifics of the traffic dataset and training data percentages are listed in the relevant table in the paper, and they are presented on this slide very briefly. The initial analysis were performed by considering the relative error average, providing an average value of the deviation between the estimated and real cardinality changes of the source and destinations. These results are shown in the figure and in figure 5 in their paper. Parameters xi and yi are the rows and columns in a two-dimensional bit array hi, where I is between 1 and z. It is observed that the relative error decreases as x increases. Similarly, it also decreases with increasing y. This suggests that the estimation accuracy is improved with increasing xi and yi owing to the hash collision reduction. Moving on, the false positive rate and false negative rates, FPR and FNR, were used to compare the AH identification accuracy of CSE, DCDS, and the present ARS method on the test datasets. C5 was trained on two sets combined to predict beta and alpha, which was 2.45 and 0.295 respectively. The average values of the test sets for each approach are again represented in this figure and in figure 6 in the research paper. It was observed that the FPR decreases with an increase in theta, owing to false positive generation due to abnormal host address reconstruction. Similarly, the FNR of ARS also fared well in comparison with the other approaches and decreased proportionally with increase in theta, owing to accurate cardinality change estimation. Afterwards, ARS was applied to the real-world QIDA DDoS attack dataset, validating and comparing the FPR and FNR with variation in theta with a predetermined beta of 4.45 and alpha of 0.185. Because QIDA primarily caters to DDoS traffic, the collected normal dataset from sets 1 and 2 were combined with the QIDA set to analyze the functionality and relevance of AHID approaches. The results are shown in figure and in figure 7 in the paper. It can be readily observed that ARS provides improved AH identification accuracy in relation to other methods by a factor of 0.5 to 0.8 or 32 to 46%. And the primary reason for the improvement in accuracy is the ML-enabled calculation of threshold parameters alpha and beta using training data and efficient reconstruction of source and destination addresses, which reduces the overall false positive and false negatives. So to conclude in this paper, we introduced a novel machine learning enabled adaptive reverse sketching method for abnormal host identification. And we use training data to dynamically predict and specify cardinality change thresholds. The data structures were extracted from network-wide nodes, compressed, and then filtered to optimize memory and transmitted to analytic servers. A simultaneous operation was performed thereafter to ascertain the cardinality changes associated with the source as well as the destination to identify abnormal hosts. And ARS proved highly efficient in discriminating abnormal hosts when evaluated on real-world datasets in comparison with other approaches. So thank you very much for listening. If you have any questions or comments, please feel free to email me on this address. Thank you.